You ever see a piece of heavy machinery at work and just wonder, how does it not just, tip right over? Well, today we're going to pull back the curtain on the hidden physics of a machine a lot of us see all the time. Okay, let's dive into this seemingly simple task and uncover the complex balancing act that's happening right under our noses.
So here it is, a tractor lifting a super heavy scoop of gravel. I mean, this is a job done thousands, probably millions of times a day on farms and construction sites everywhere. But what we're really looking at here is a classic physics problem. It's a delicate dance of weight and leverage and force that engineers have to get absolutely perfect to keep things safe and stable.
And that is the big question we're going to answer today. How does it stay balanced? It's not magic, not at all. It's physics. So what are the invisible forces pushing and pulling on this machine to keep it from just planting its nose straight into the dirt? Let's break it all down.
Okay, first things first, let's get the setup right. Before we can solve anything, we gotta think like an engineer. And that means we need to clearly define the problem, lay out everything we know for sure, and then figure out exactly what it is we're trying to find.
So here's our challenge. We know the tractor itself weighs 2,100 pounds. And that scoop of gravel, that adds another 900 pounds. All of that weight is pushing down, down, down. Now, obviously the ground has to push back up to support it, but how is that force spread out? Our mission right now is to find the exact upward force on those rear wheels and the exact upward force on the front wheels. We're going to solve for those big question marks.
Now, to find those forces, we can't just take a wild guess. We need a toolkit, a set of fundamental principles in physics that basically govern any object that's standing still. It's all about making those unseen forces, well, visible.
And the very first tool an engineer grabs is simplification. Seriously, they don't work with some super complicated drawing of a tractor. No way. Instead, they strip away everything that's not essential and create what's called a free body diagram. It's basically a super simple sketch that shows only the object itself and the forces acting on it.
So our whole tractor, with all its moving parts, just becomes this: 4 simple arrows. That's it. We've got 2 forces pointing down, the tractor's own weight pulling from its center of gravity, and the gravel's weight pulling down from way out at the front. And to fight against all that, we have 2 forces pushing up from the ground, one at the rear wheels and one at the front wheels.
And now for the core of our toolkit, the 2 non-negotiable laws of balance, the equations of equilibrium. First, all the up forces have to perfectly cancel out all the down forces. Makes sense, right? Otherwise, the tractor would either be sinking into the ground or launching into space. And second, just like a perfectly balanced seesaw, all the rotational forces, the forces trying to tip it over, they have to cancel each other out too.
All right, we've got our problem, we've got our tools. Let's get to the main event. Let's actually run the numbers and figure out exactly how this tractor is pulling off this incredible balancing act.
We're going to be smart about this. We have a 2-step plan. First, we're going to tackle those rotational forces to figure out the force on the rear wheels. Then, once we've got that number nailed down, we'll use our first rule, that ups have to equal downs, to very easily find the force on the front wheels. It's a clean, simple, 2-step process.
You want to know the real trick to solving this whole thing? It's all in step 1. We can make the problem so much simpler by picking one spot to be our pivot point, our fulcrum. In this case, we're going to choose the front wheels. It's like we're freezing the whole seesaw right at the front axle and asking, what forces are trying to make this thing spin, and what force at the rear wheels is stopping it? So think about that seesaw. The tractor's own weight, which sits behind the front wheels, is actually trying to tip the tractor backward. But at the same time, that super heavy bucket of gravel way out at the front is creating a much stronger force trying to tip it forward. And the only thing stopping it from face planting is the upward push on those rear wheels. It's a constant tug of war.
So, when we do the math and balance those 2 competing spinning forces, the tractor's weight pulling it back and the gravel's weight pulling it forward, we can calculate the exact force needed at the back to keep everything perfectly still. So what is it? What's the upward push on each one of those rear wheels?
325 pounds. That's the magic number. The ground is pushing up on each rear wheel with exactly 325 pounds of force to stop that tipping motion. And just like that, the first half of our puzzle is solved. Now that we have that number locked in, the rest is easy.
All right, now for the easy part. We know the total downward force is 3,000 pounds, right? That's the 2,100-pound tractor plus the 900 pounds of gravel. And we just figured out that the two rear wheels are supporting a total of 650 pounds together. So what does that leave for the front wheels to handle?
1,175 pounds, and that's per wheel. Whoa, that is a massive difference. I mean, think about it. The front wheels are supporting way, way more weight than the rear wheels. And that isn't just a number on a page. That has some huge implications in the real world.
So, okay, we solved the problem, we got the numbers. But what does it all actually mean? Why do engineers spend so much time calculating these forces with this much precision? Let's connect the math back to the actual machine.
Just look at these numbers side by side. It's incredible. The front axle is supporting over 3.5 times more weight than the rear axle. This isn't just a small shift, it is a colossal transfer of the system's entire load, and it's all focused right on the front of the vehicle. The tractor is basically pivoting on its front wheels, and the rear wheels are just there to keep it from tipping all the way over.
So here's the big takeaway. Lifting that scoop of gravel completely changes the physics of the tractor. This calculation tells engineers that the front axle, the wheels, the tires, they can't just be strong, they have to be engineered to handle immense, concentrated stress. It's what tells an operator the safety limits they have to obey to avoid a catastrophic tip-over. And hey, this isn't just about tractors. These exact same principles, this idea of static equilibrium, this is what keeps 1,000-ton cranes from falling over, and what allows bridges to carry traffic safely for decades. It is the invisible science holding our world together. So the next time you see a piece of construction equipment, or a suspension bridge, or even just a simple ladder leaning against a wall, remember that invisible balancing act that's happening. It kind of makes you wonder, what other unseen forces are out there quietly at work, keeping our world from falling apart?